Welcome to this next lecture on acoustics. We have all the material now. We have the appropriate Green functions, the Neumann and Dirichlet Green functions. To solve some typical problems. But before I do that, I just want to make sure it was clear what we were doing, okay, with regard to finding these Green functions. So let us say for the exterior Neumann Green function, our free space Green function was G R dash given by minus I k summation n going from 0 to infinity j n of k r h n of k r dash summation m going from minus n to n y m conjugate n theta dash phi dash y m n theta comma phi. Okay, so r dash theta dash phi dash are the receiving points, r theta phi are the source points. Okay. Now we were going to find a homogeneous solution, okay, that is actually only a function of r dash, okay, and we wrote it in this form I k summation n 0 to infinity the Hankel function k r dash j n dash k a h n dash k a Hankel function of k r summation over m y m conjugate theta dash phi dash y m n theta phi. Now in here the r theta phi do not participate in any partial differential equation. So del square plus k square g h is 0, where this is composed of r dash theta dash phi dash independent variables. So r theta phi are just dummies, they are just added so that this combination goes to 0. So now if I do del g by del r, okay, which will be taken onto a sphere r equal to a, then I get minus I k square, this is undergoing the differentiation, summation n j n dash k a, Hankel function is there, k r dash the receiving point, then summation m is equal to minus n to n y m n conjugate y m n. And if I do del g h by del r and evaluated it r equal to a, I get this undergoes the differentiation. So I k square n 0 to infinity Hankel k r dash j n dash k a by h n dash k a and h n dash k evaluated ray on the sphere, and so this is m summation y m conjugate n y m n. So this cancels off. Now you can see that this is just the negative of the other. Okay. So now if you sum these two, it goes to 0. That means the sum g plus g h, which is a new Green function g n, and del g n by del n of this, or del g n by del r of this, because we are on a sphere, that goes to 0. This summation goes to 0. The g and gh in the derivative are negative to each other. Okay, that's the idea. So this is indeed a solution to the homogeneous wave equation in spherical coordinates with r dash, theta dash, phi dash. Okay, and because we have a Hankel function here in the far field, it will be of the second kind. It's a far second kind. It will be propagating outward, and so the Sommerfeld radiation condition is satisfied. Okay, it's exterior. It's an exterior Dirichlet, Neumann Green function. So exterior to a surface in the long distance. This is an outgoing wave, so it satisfies the Sommerfeld radiation condition. So that's the idea, and this idea went through all the Green functions, interior or exterior. Okay. Now another thing I say is that I am following the e to the power plus I omega t way of deriving. Okay. Some people choose the e to the power minus I omega t. There is also, you will find work related to this negative sign also. It's quite common. Okay. However, I am sticking with plus j omega t. Okay. Now the exterior Neumann Green function actual form is this: g n r r dash, okay, evaluated of course on a sphere, is given by minus 1 by k a square summation n Hankel k r dash, this is n, okay, this is Hankel, and Hankel n dash k a and double sum. Y m conjugate n theta dash phi dash y m n theta phi. So r theta phi will be the source coordinates, or r equal to a theta phi will be the source. R dash theta dash phi dash will be the receiver points or measurement points. Okay. Now we will look at this problem here, which is called a pulsating sphere. We will do this first using a Neumann Green function approach, pulsating sphere. So what it is a sphere of nominal radius, let us say a, and then there is an oscillation on top of it, delta of t, uniformly for all theta and phi. So it bulges and it contracts. Okay, it's like a breathing cavity. It uniformly bulges and uniformly contracts inward. That is why it is called a pulsating sphere. This is a typical model of a acoustic speaker. One simple model speaker. Okay, so it pushes the volume of air around it so that the density change occurs, and from there the pressure change occurs and a sound wave is generated. Okay, and it is symmetric all around theta and phi. Now what is the sound field due to this? We will find the mathematical answer using this. Okay. Now why is this useful? Because if we look at the kh integral, its phi, let us say at r dash, is the integral of g del phi dot n minus phi del g dot n, okay, over a surface. So del g dot n, if we choose this, is 0 on a sphere, just like this sphere of radius a. Okay, so this is going to be an integration on a surface of a sphere. So then this del g dot n is 0 from what we have derived for the exterior Neumann Green function. So we are left with only g del phi dot n. Okay, so now what I have is phi at r dash is equal to integral over surface, spherical surface of radius a and g Neumann del phi dot n and integration over the sphere. Okay. Now if phi is any function, then here also phi is any function phi. But if I make this pressure, if I choose this to be pressure here, then on the right hand side also it becomes pressure. Gn r equal to a r dash, then del p del n and ds over r. In fact r is equal to a here. So this ds has the form a square sin theta d phi. Okay, we are on a surface, mind you, there is a surface element on a sphere. Now if we are looking at an exterior problem, then my n points this way, but my r points outward. Okay, so del p del n is equal to minus del p del r, and the Euler equation says del p by del r is equal to minus j omega rho velocity r. Okay. So now we have del p del r at r equal to a, and therefore Vr is at r equal to a. So first of all, del p del n changes sign if I replace it with del p del r. Then del p del r with a minus comes this term which also has a minus. Okay. So my p at r dash location is given by the integral over a sphere of radius a gn, okay, r equal to a and r dash theta dash phi dash then double minus j omega rho and Vr, velocity on the surface. So, we said this is a uniformly pulsating sphere. So, the surface element uniformly expands out and goes back in. So, that velocity we will call it as u0 e to the power j omega t. This is velocity and this is the harmonic. Okay. So, the surface moves in and out harmonically. This whole course is about harmonic oscillations. Okay. So, j omega rho u0 and then a square sine theta d theta d phi. Okay. So, if I substitute for the Green function, the Neumann Green function, okay, so I will get pressure at r dash is equal to integral 0 to pi integral 0 to 2 pi. Okay. The Green function has a negative in it. We have brought in 2 more negatives. So, we will hang around with a negative minus I omega rho u0, let us say, divided by k a square summation over n Hankel function k r dash by Hankel function dash of k a m summation y conjugate summation and y summation. Now, the area element a square sine theta d theta d phi. Okay. Now, just to help us finish this thing, we should recall that y 0 0 theta comma phi, okay, is equal to 1 over square root of 4 pi y 0 1 theta comma phi is equal to root over 3 by 4 pi, okay, and then lastly y 0 n theta comma phi is equal to root over 2 n plus 1 by 4 pi p n cos theta. Okay. Now, we should remember the ultimate expression perhaps also. Ymn theta comma phi is given by square root over twice n plus 1 by 4 pi n minus m factorial by n plus m factorial p m n cos theta e to the power I m phi. Okay. So, that when we look at this 0 to twice pi y m n theta comma phi d phi, we subject it only to the phi integral and phi is there only here. This will be non-zero only when m equal to 0. So, this will approach for values of m equal to 0, this term cancels. So, we will end up with twice n plus 1 by 4 pi p m n cos theta, okay, delta m0 into 2 pi. Okay. When m is 0, This is just 1 and it gets integrated from 0 to 2 pi. So, I get a 2 pi, that is this 2 pi, and m is forced to be 0. So, this m will be forced to be 0, and then if I take a look at this 4 pi and that 2 pi, this comes in as 4 pi square inside. So, 4 pi cancels as a pi. So, I get root pi twice n plus 1. Let me use the delta p0 n cos theta delta m0. Okay. So, if I write now p at r dash theta dash phi dash location as equal to minus I omega rho u0 by K s square, okay, and then the phi integral has given me let us say, so the phi integral is over, only the theta integral is left. Okay. So, if I look at it, I have summation over n Hankel n k r dash by Hankel n dash k a, and then now if I bring this in here, I had a summation over m, okay, then y m conjugate n theta dash phi dash, but the ym and integral of phi gave me root over pi 2n plus 1 p0 n of cos theta delta m0. Okay. So, what happens, this m must be 0 comes in, applies here and applies here. So, we are left with one term, and here I have k is equal to omega by c on top. So, I get minus I rho c u0, and okay, sorry, that's something I missed here. Okay, I have an integral over theta still left. Okay. So, I will put it somewhere here, let us say 0 to pi a square sin theta d theta. So, this a square also goes with that a square. Okay. So, I am left with minus I rho c u0 summation over n Hankel k r dash by Hankel dash of k a. Okay. Now, m is equal to 0 must be chosen. So, I will end up with integral 0 to pi y n theta dash phi dash, okay, or y0 conjugate n theta dash phi dash, then root over pi twice n plus 1 p0 n cos theta sin theta d theta. Let me take this to the next page first, and we will sort it out again. In here, I will delete some unnecessary things. Okay, so let me write it properly now. P at r dash theta dash phi dash is equal to, let me take this up, Okay. Then I have y0 conjugate n theta dash phi dash, which does not come under theta integral. I have an integral over 0 to pi. Okay. In fact, let me just put this constant also outside. This constant root over pi into 2n plus 1 also outside. Okay. Then I have an integral. I have an integral 0 to pi Pn cos theta sin theta d theta. Okay. That is the expression. Now, if we say that there is a 1 over here, the value 1 over here, okay. So then P0 cos theta is 1, okay. And what I have for Legendre polynomial orthogonality is integral Pmn dash cos theta Pmn cos theta sin theta d theta is equal to 2 over 2n plus 1, okay, n plus m factorial by n minus m factorial into delta n dash n. So, these two must be same. In here m is 0, m is 0. If m is 0, this term entirely cancels, okay. And now the 1 is P0 of cos theta. So, let us say n dash is n and this n is equal to 0. That is what we have here, Pn cos theta and a 1. So, now this delta and n dash will be delta n and 0, okay. So, this will, and n is 0, right. So, this will be 2 by 1 delta n 0, okay. So, now what happens here? I have, let me write this again, r dash theta dash phi dash minus I rho c u0 summation over n Hankel n of kr dash by Hankel n dash of ka, then y0 conjugate n theta dash phi dash, then root pi 2n plus 1, and this thing is twice delta n 0, okay. So, this delta n 0 means n must be 0, we will take out this n, we will make this 0, and from here keep only the n equals 0 term, okay. So, that is interesting. So, what will happen now? Minus I rho c u0 Hankel 0 kr dash by Hankel n dash of ka, okay. Then y0 conjugate 0 theta dash phi dash root pi, because n is 0, into 2, okay. And we saw that y00 is 1 by root over 4 pi. So, this is 1 by root over 4 pi and this is root pi. So this goes, then root over 4 is 2, so 2 goes with 2. Okay. So what am I left with? Minus I rho C U 0 Hankel 0 Kr dash by Hankel n dash of Ka. And let us look at Hankel 0 and Hankel sorry, this n will also be 0 here. Okay, this will be 0. Why? Because delta of n 0. Now let us look at Hankel 0 and Hankel 0 dash. Hankel function 0 second kind x is given by e to the power of minus I x by minus I x. Okay, and Hankel function 0 dash of x is, let us say, I will keep it outside, minus I e to the power of minus I x by x, okay, minus 1 by x square e to the power of minus I x. Okay, so this gives me minus I x square x I plus 1 e to the power of minus I x. Okay, so then Hankel 0 dash of Ka is minus I Ka plus 1 by k square a square e to the power of minus I Ka. Okay, we have come a long way. So let us do this. We will complete this problem in the next class. Okay, I will stop it here for now. Thank you.